Hello everyone. So today we'll be talking about binary search tree. So binary search tree was originally invented in 1960 for storing labeled data on a magnetic disk. So before you learn binary search tree, these are a few topics you need to understand. Binary search on a sorted array, big O complexity, and basics of a hash table. So once you understand these three, you are ready to learn binary search table. So today we'll be learning in this order. These are the topics we'll be covering. So first is the need for binary search tree. Where would we use a binary search tree? So if you have a collection of comparables mean where you can compare two items, like integer is a comparable where I can say between 4 and 5, 4 is small, 5 is big, or between 2 and 2, both are equal. So if you can compare two items and say they are big or small or equal, that's a comparable. So if you have a collection of comparables and you want to be able to find on those comparables very quickly, that is a place where you will use binary search tree. So these are all the things you can do on a binary search tree. You can find the min, you can find the max, you can find the closest key if the key you're looking for is missing. So now you might ask, you can do all of this in a sorted array. Like you can find min, which is the minimum index, which is if you want to find max, that's the maximum index. If you want to find an item, you can do a binary search and find it in big O of log n. So why do we need a complicated structure like a binary search tree? And the reason for that are these operations, insert and delete. So if you want to insert something into this array, you'll have to copy all the items into a new array, which is one size bigger. Similarly for delete, if you want to delete an item, you'll have an array which is one size smaller and copy over all the items. So copy over all the items means you have to go through all the items, which is big O of n. And binary search tree can do both insert and delete in big O of log n. We'll see that later, but it can do insert and delete in big O of log n. So if you have an application, so let me correct one part, that big O of log n if it's a balanced binary search tree. So today we won't be talking about how to balance a search tree. We are just going to be assuming it's balanced. Balanced means every node has two kids except for the bottom row. So for a balanced binary search tree, insert and delete are big O of log n. So if you have an application where you have to keep adding and removing items, that is one place where you will use a binary search tree. In your application, suppose you are given a one-time set of set of comparables, and once the application loads, you don't have to insert or delete ever again, and you just have to find. In that case, you will just use a sorted array. But if you have a lot of inserts and deletes, this is the right choice. So now we talked about the need for binary search tree, which is if you need insert and delete on a list of comparables, on a collection of comparables. Next is binary search tree versus a map. So map, you can find items very quickly by the key. So if your use case is only to find item by a key, then you will use a map, not a binary search tree, because here a find takes big O of log n, but on a map a find is constant time. So if it's only find, you will use this, but if you need these operations, you will use binary search tree. A real life example. A real life example is B tree. So B tree is a form of balanced search tree. It's not a binary search tree. It's a form of balanced search tree, but to understand that, you would have to first understand a binary search tree. So this is the precursor for understanding a whole lot of balanced search trees, like red black. That's again a balanced search tree with many applications. But before you understand that, you need to understand this. And also another need to understand this very well is if you're preparing for interviews, a lot of questions in interview, like a medium level question, are based on binary search tree, particularly in the phone screen interviews. So this is very important to master. So after a real life application, so real life application, like I said, is a B tree which is used to store indexes for a relational database. So that is one of the examples. Now let's look at the operations. Before we look at the operations, actually let me tell you this. So all of these are nodes. So this is how a node looks like. A node has a left child, which itself is a node, right child, which is also a node, parent, which is also a node. So this is something you need to remember. I will erase this in a bit, but before I erase this, either take a note of this or try to remember this. Every node has a left child, a right child, and a parent. So like this node has a left child, which is a node, right child, which is a node, and parent, which is again a node. And what makes a binary search tree is two invariants. For every single node, all the nodes on the left are smaller than that node. Like for 18, 12 is smaller, this is smaller, everything on this side is smaller. Like even if you pick 15, left side, everything is smaller. 12, left side, everything is smaller. And also everything on the right is bigger. Like 18, this is bigger, this is bigger, this is bigger, this is bigger. So everything on the right is big, everything on the left is small if you're not allowing duplicates. If you allow duplicates, you can pick either side where you want to enter the duplicates. In my case, I picked left side, but while writing your search tree, you have to pick one and just stay consistent. So in my case, I'm adding duplicates to the left side. So in my case, everything on the left is smaller or equal and everything on the right is bigger. So an easy way to remember, everything on the left small, everything on the right big. So those are the two invariants. So I'm going to rub this and this off. So if you want to take a note or remember this, either way it's fine. So first operation we are going to look at is an insert operation. So one thing to remember, in a binary search tree, you just have a reference to the root, which is the top parent. You don't have a reference to any other item. So anything else you need to operate on, you have to start at the root and find the item you need. So now assume your algorithm starts, and right now your tree is empty and you get a new number, say 18. So what you will do is you will first check whether the root exists. In this case the root is null, so we will add the first element as root, which is 18, and this will be our root. Now when we get the second item, say 12 comes, I started root, compared to 18, 12 is smaller, right? So what we learned in invariant is anything that's smaller goes to the left, anything bigger goes to the right. So since 12 is smaller than 18, add a left child, 12. Then I get the next number, 25. Again compared to 18. 25 is bigger than 18. And anything bigger goes to the right. Add a right child, 25. Again next item comes, 4. Compare it with 18, smaller, 4 will go to the left. Compared to 12, smaller, 4 will go to the left, and here no more left child, so I'll add here as 4. Next item I get 15, compare, smaller than 18 goes to the left. Compared to 12, it's bigger, go to right. Now there is no more right child here, I'll create a right child, 15. So insert is pretty simple and straightforward. You just compare and go left, right. So one more example. So say I get another number 25. Come here 18, bigger than 18 goes to right. Now what we decided is we are going to allow duplicates. So if we come across 25, we are just going to create a left child and add it there. But it depends on your search tree. If you want, you can disallow duplicates also. So that was insert. Now next we'll look at search. So search is pretty much very similar to what we did in insert. Suppose I want to find number 15. I start at the root, compare it to this one. It's smaller, 15 is smaller, so if it exists, it will be on the left side. Go to the left. compared to 12. Now 15 is bigger. If it exists, it's going to be on the right. Come here, found 15. Now let's say look for a number that does not exist. Say 13. Oh well, 13 exists. Say 16. I'm looking for 16. So let's see what happens. Come here, compare 16 to 18. 16 is smaller. If it exists, it will be on the left side. Come here. 12. Compared to 12, it's bigger. If it exists, it will be on the right side. Come here. 15. If it exists, it will be on the right side because it's bigger than 15. Come here. 17. Now if it exists, it's going to be on the left side because it is smaller than 17. Come here. No more. So your search ends here because you reach a null reference, so you know that the key does not exist anymore. So that was search. Now next we look at min and max. So min and max is very simple. For min, you just go left, 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 left until you reach a null pointer. That is your min child. So say I start here, go left, left, left. Okay, now in this case there is no more left, so this is my min. And similarly for the max. Okay, here I missed one number. Similarly for the max, you just keep going right until you can't go right anymore. So for this one, start at the root, go right, go right. At this point, I can't go right anymore and this is my max. So min and max is very simple. Next, we are going to see closest key. So binary search tree has this additional property where if a key does not exist, you can find its closest keys. So that is important to remember. The key should not exist. Like if I'm looking for 18, 18 exists, so I cannot find closest keys. I mean, I can find, but it won't be login. But if you are looking for say 27, now 27 does not exist here. So in case 27 existed, the closest keys would be 25 and 28, right? So 27 does not exist, and if it doesn't exist, I can find its closest key, and the way to do that is you search for that number. And when you search for that number, if that number does not exist, you will encounter the biggest key smaller than it and the smallest key bigger than it. So say if biggest key smaller than this, 27 is 25, smallest key bigger than 27 is 28. So you just have to keep track of those two items. So search for 27 pretending it exists and just keep track of what is the item just smaller than 27 and just bigger than 27. So let's try that. So say I'm looking for 27 compared to 18. If it exists, it will be on the right tree. But now I know 18 is smaller than 27. Track it here. Come here, 25. If it exists, it will be on the right side. But then when I hit 25, it's smaller than 27. So from the lower side, that is closer to 27. Track that. 27. Now I say 27 exists, it will be on the right. Come here, 30. 30 is bigger. Track it. If it exists, it will be on the left because 27 is smaller. Go here, 28. 28 again, from coming from above, it's closer to 27. 28. Now if it exists, it's on the left, it doesn't exist. So now we found both 25 and 28. So again, let me write it down. What you do is you track these two elements. The biggest smaller than the number, which is this is the biggest smaller than 27, and the smallest bigger than the number. So this 28 is the smallest bigger than 27. So now we've looked at closest key also. Now delete. Now delete. In delete, there are three use cases. You delete a node with no children, node with one child, and node with two children. So these are the three use cases. So like any operation, the first thing we'll do is find. So let's say we want to delete 3. First we will find 3. Come here. 3, if it exists on the left. 3 smaller than this, go left. 3 smaller than this, go left. 3 bigger than this, go right. Okay, found 3. 3 has no children, so you can just right away delete it. When I say delete, all you do is for this guy, for its parent, set the right child as null. And for this guy, 3 itself, set its parent as null. So that is practically deleted. By the way, all these operations, I have code in the description below, Java code. So next is node with one child. Now suppose we want to delete 1. Okay, come here. 1 smaller, go left. 1 smaller, go left. 1 smaller, go left. Found 1. Now you cannot delete it right away because like we did earlier, because then 3 will be an orphan. So the way you delete a node with one child is you replace the parent with the child. So you just take 3 and put it here. So your tree will end up looking like this. This is how your tree will end up looking. So let me put that back. So the way you would do that in code is for this guy's parent, set the left child to this one's parent to this, and this guy set parent to null, right side to null. So this will be effectively deleted and this will come here because this guy's parent will be 4, 4's left side will be 3. So you just take it and put it here. So both these are straightforward. Now next is with 2 children. So this is slightly tricky but not complicated. So what you do, say suppose I want to delete node 12. So what I do is first I find it, go to the right and find the smallest child in that route. So I will come here 12, go right 15, and 15 smallest child, like we did from here, we just go left to find its smallest child. So I keep going left until I reach a null. So this is 13 doesn't have a left child, so that's the leftmost I can go. So this is the smallest on the right tree. So once I find the smallest on the right tree, I take this key and copy it here. So replace 12 with 13. So I replace, I'm just keeping this here to track when I revert it back. So you take that smallest child and you replace it with 13. Okay, so now 12 is gone, but now next what we do, we delete this node itself. Now this node has only one child, so we already saw how to delete a node with one child. We just take this and put it here. So we know that that's pretty straightforward. So let me put this back the way it was for the other operations. So now you might think, how do I know that this has only one child? The reason I know that this has only one child because I kept going left until I couldn't go left anymore. So I know for a fact that this guy does not have a left child. So that is how I can, I know that this has either one child or no child. So it either has a right child or it has no children at all. So now we've covered all 3 deletes. Node with one child, no child, one child, 2 children. So that covers delete. And like I said, all the code is there in the description. I uploaded it to GitHub. So we've finished these operations. Next, we're going to look at in-order traversal. So if you want to print all the items in a binary search tree in sorted order, you will do something called an in-order traversal. So the way you do an in-order traversal is for every node, you do go left, and then for You can say print itself or visit itself. I'm going to say print, some people say visit, but whatever you want to call it. Print yourself, go right. So for every single node, you go left until you can't go left anymore. When you can't go left anymore, you print yourself, and after that you go right and do the same thing. Go left until you can't go left anymore, print yourself, go right. So let's see that in action. Suppose I start, not suppose, I have to start at the root. So I start at the root, go left, I have to keep going left until I can't go left anymore. Go left, reached here, can't go left anymore. So, sorry, I rubbed that out. Go left, print yourself, go right. Go left, print yourself, go right. So you come here, cannot go left anymore, I'll print myself, 1. Then go right. Now again the same thing. Keep going left until you can't go left anymore. There's no more left here. Then I come back here, print yourself 3. Go right, I can't go right anymore. And this code is done using recursion. So once you've done here, you come back here. Now for this node, you've done all 3. Go left, print yourself, go right, you come back up here. Now for this node, you've done go left. Next is print yourself, which is 4. Then go right, you cannot go right anymore, you go back up here. Now for node 12, you already done go left, that part is done. Go left is done. Next is print yourself, it will print 12. Then go right. So 1, 3, 4, 12, yeah. Again for this node, go left, cannot go left here, print yourself 13. Go right. Here again go left, cannot go left anymore. Print yourself 14. Go right, cannot go right. So comes back up here, comes back up here. Now this guy has already done go left. Now it's turn to print yourself, which is 15. Go right. Here cannot go left, comes back up here, print yourself 17. Go right, cannot go right. So now this guy has done all of it. Go left, print yourself, go right. So you come from here, this guy has done all of it, you come back here. Now this has also done go left, print yourself, go right. So it goes back up here. Now this guy has done go left, his turn is print yourself, which is 18. Go right. Again go left, cannot go left anymore, print yourself 25. Go right, cannot print in, no more go right, comes back up here. Now this guy has done go left, next is print yourself 25, go right, and so on and so forth. So basically, like you see, it's in sorted order. 1, 3, 4, 12, 13, 14, 15, 17, 18, 25, 25. Yeah. So this is in sorted order. So this is called an in-order traversal. So this is also a very popular phone screen question for interviews. So next, so we've covered all of this. Next, we'll do complexity analysis. Again, for any interview, especially in Bay Area, any algorithm, they will always ask for space and time complexity. So let's look at the space complexity. So space complexity is how much memory do you use compared to the size of the input. So input size is n. So for every time when you do big O, input size is n. That's the common notation. Or size of the input. So both for space and time complexity, you have to relate it to the number of items. So that's how big O works. So big O for space complexity is big O of n, and I'll tell you why. It's big O of n because you need as many nodes as the number of items. So you don't have to calculate the actual memory used, you just have to relate it to n. So as much n, that many number of nodes. So big O of n is the space complexity. So suppose you needed half the number of nodes, it will still be big O of n. If it's logarithmic, then it will be log n. But anyway, let's in this case none of that is true. So to keep it simple, yeah, the space complexity is big O of n. Now next is time complexity. So time complexity is a little bit more tricky. So the time complexity, like I said in the beginning, for insert, search, delete, for a balanced binary search tree, that's important, okay? It's for a balanced. If it's not balanced, it's not true. For a balanced binary search tree, insert, search, delete is all log n. Now I'll prove it to you. Why is it log n? So first thing you have to observe, okay, before I proceed, let me tell you one definition. Depth. So depth is the distance from the root. So here depth is equal to 0. Here depth is equal to 1. Here depth equal to 2. So depth is the distance from the root. So maximum depth here is 4. So depth equal to 3 and depth equal to 4. So one thing to observe here is whether you do insert or you do max or min or delete or search, any of these operations, the maximum number of nodes you'll have to touch is proportional to the depth. Like suppose I'm finding cell element, the maximum I will go down is 1, 2, 3, 4. After that, I won't go down anymore, right? So the depth, maximum depth is what its time complexity depends on. So all these operations are related to the maximum depth. So I already know the time taken depends on the maximum depth. Now if I can relate the number of elements to depth, I can relate the time taken to the number of elements, which is the ultimate goal for time complexity. So let me show you how that's calculated. So at any depth, the total number of nodes at that depth is 2 raised to depth, right? So here the total number of nodes is 2 raised to 0, which is 1. Here the next depth, total number of nodes is 2 raised to 1, 2 raised to d, which is depth is 1, 2 raised to 1. Next level, there are 4 nodes, which is 2 raised to 2. So if I were to find the total number of nodes, it will be n is equal to 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2 plus until 2 raised to d, where d is the maximum depth. So now if you look up geometric series, there is something called the geometric series. So I'm not gonna solve this and find the equation. You can look it up online. So in the geometric series, they say a plus ar plus ar square plus dot 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 a into r raised to n minus 1 is equal to a into 1 minus r raised to n over 1 minus r. Let me just confirm that. A into 1 minus r raised to n. Yeah. So this is what is called a geometric series. So I'm just going to use that over here. So this part, I'm going to simplify it using geometric series. So here my a is equal to 1, my r is equal to 2, and my n is equal to, actually n minus 1 is equal to d, which means n is equal to d plus 1. Let me confirm that also. A is 1, r is 2, n minus 1 is d. Write it clearly. N minus 1 is d. Yep, so n is equal to d plus 1. So now if I substitute this in the equation, a is 1, r is 2, and n minus 1 is d, which means n equal to d plus 1. I can replace this whole with this one, right? So n is equal to a into r raised to 1 minus n. A is 1 into 1 minus r raised to n, 1 minus R is 2, yeah. 2 raised to n is d plus 1. Minus r raised to n over 1 minus r, which is 1 minus 2. So this is how, using a geometric series, right side, this is how my equation comes out to. Now this thing, if I solve further, this becomes, so this is what I have right now, n is equal to 1 multiplied by 1 minus 2 raised to d plus 1 over 1 minus 2. So this comes out to n is equal to 1 minus 2 raised to d plus 1 over minus 1. So this becomes minus n is equal to 1 minus 2 raised to d plus 1. And that becomes 2 raised to d plus 1 equal to 1 plus n. And that is taking log on both sides. D plus 1 is equal to log of n plus 1 to base 2, which means d is equal to log of n plus 1 to base 2 minus 1. So d is the depth. So d is equal to this, which means d is approximately proportional to log of n. I mean, if we simplify this, it's approximately equal to log of n to base 2. And I already know the time taken by my operation depends on the depth, which is d. So time taken depends on d, which means time taken depends on log n. So that is how I know my time complexity is log n, both for insert, search, max, min, closest key, delete. For all of them, my time complexity is log n for a balanced search tree. Again, remember that it's a balanced search tree. If it's not a balanced search tree, this won't be true. So I think I've covered everything that I needed to cover today, and the code again can be found in the description. Thank you.